Okay, let's dive right into this explainer. We're looking at hematology, the body's fluid highway. Right at this very second, there's a highly organized biological highway system flowing inside you. We're talking about the physiology of blood, how it literally heals itself, and why it's absolutely crucial for keeping everything in your body balanced and alive.
To understand this whole system, we're going to hit 5 main stops today. We've got 1, the fluid highway, 2, the cargo fleet, 3, immune security, 4, emergency repair, and 5, passport control. Let's get to it.
Section 1. The body's fluid highway. So let's start with the infrastructure itself. We're talking about the literal rivers and roads making up this vital connective tissue. Blood is way more than just red liquid, you know? It's a highly specialized fluid connective tissue regulating your body's most fundamental baselines.
To put things in perspective, a healthy adult male carries about 5 to 6 liters of blood, and females carry around 4 to 5. And man, this fluid is maintained under incredibly strict conditions. It stays at a warm 104.4 degrees Fahrenheit, which is actually slightly warmer than your core body temperature, and it operates at a very, very precise, slightly alkaline pH, right between 7.35 and 7.45. Even a tiny deviation from those numbers, yeah, that spells serious trouble.
Now, if you were to spin a vial of blood in a centrifuge, it actually separates super neatly. Exactly 55% is the liquid blood plasma. Think of this as the roadway. It's mostly water, but it's packed with plasma proteins and dissolved nutrients. And that remaining 45%? Those are the formed elements. Basically, the actual cellular traffic navigating those plasma roads.
All right, Section 2, red cells, the cargo fleet. Moving into our first real department here, we've got the erythrocytes, or red blood cells. These guys act as the specialized delivery trucks of our highway, and they make up the vast, vast majority of that cellular traffic.
These cells have an absolutely brilliant physiological design. They've got this biconcave disc shape, kind of looks like a donut where the hole didn't get punched all the way through, right? This naturally increases their surface area for trading gases. But check this out. To get maximum internal space for cargo, they actually ditch their nucleus as they mature. Plus, no mitochondria, meaning they generate ATP anaerobically, so they don't accidentally consume the precious oxygen they're supposed to be delivering. Talk about efficiency.
And that extra internal space, it is absolutely critical. Why? Because a single erythrocyte contains roughly 280 million hemoglobin molecules. 280 million. Hemoglobin is the protein complex doing the actual heavy lifting here. Every single molecule has 4 heme pigments, and each of those holds essential iron ion that binds directly to oxygen. So the catch here is that these hardworking trucks have a lifespan of about 120 days. After 4 solid months of circulating and literally squeezing through microscopic capillaries, they just get worn out. At that point, they're gracefully pulled off the road and recycled by fixed macrophages in your spleen, liver, and bone marrow. This way, the iron can be fully reused for the next generation of delivery trucks.
Moving on, Section 3, white cells, immune security. Now we meet the leukocytes. This is the nucleated security force constantly patrolling the highway for pathogens. They're way fewer in number than the red blood cells, but their role is literally life-saving.
This whole security force is basically divided into 2 main squads based on how they look under a microscope. On one hand, we've got granulocytes. These possess visible, stained cytoplasmic granules. Think of it like them carrying visible equipment on their belts. On the other hand, we have agranulocytes, which lack those distinct granules and have a much smoother appearance. Think about the highly specialized units within these squads. It's pretty amazing. Neutrophils are granulocytes and make up the bulk of the force, around 55 to 70%. They are your rapid first responders, rapidly phagocytizing, or basically eating, bacteria. Lymphocytes, which are agranulocytes, sit at 20 to 40% and handle adaptive immunity like B, T, and NK cells. Then you have your monocytes at 2 to 8%, transforming into macrophages, eosinophils at 2 to 4%, specifically hunting parasitic worms, and finally basophils at 0.5 to 1% releasing histamine for inflammation. It is a perfectly balanced defense system.
Section 4, platelets and emergency repair. So what happens when the highway gets damaged? Say you get a paper cut, or even a more serious vascular injury. Well, that brings us to platelets and the incredible rapid response process of hemostasis.
Let's see how the body builds a repair completely on the fly. It's a highly synchronized 4-step process. First up, vascular spasm. The damaged vessel literally constricts to stem the flow. Number 2, platelet plug formation. Platelets just stick right to the exposed tissue and form a physical plug. Step 3 is blood coagulation, where it turns into a solid gel. And 4, fibrinolysis. Once the underlying tissue heals, this process kicks in to dissolve the temporary clot.
That third step, blood coagulation, is particularly dramatic. It's not just blood drying. We're talking about a complex enzymatic cascade involving 12 different clotting factors. In just minutes, prothrombin gets converted to thrombin. Then thrombin grabs soluble fibrinogen floating around and turns it into insoluble fibrin threads. It literally weaves a biological net to trap blood cells and securely seal the broken road.
All right, Section 5, blood types and transfusions. Finally, we have to talk about passport control, the ABO and RH blood group systems. Because blood is essentially an organ, you definitely can't just mix anyone's blood together. The immune system is constantly checking cellular passports to dictate who can safely share the highway.
To really put this into perspective, let's look at a clinical scenario from our source material. Imagine a 28-year-old male who needs an emergency transfusion after a severe car accident. His blood type is B negative. The question is, who can safely donate to him?
Let's look at his physiological passport. Because he's type B negative, his red blood cells have B antigens on them. And because of that, his plasma naturally produces anti-A antibodies, meaning his plasma will aggressively attack anything with an A antigen. Plus, because he's Rh negative, he completely lacks the Rh factor, so he can't safely receive Rh positive blood either.
To solve this puzzle, we have to map out the interactions carefully. If we gave him type A or type AB blood, his anti-A antibodies would bind to those new cells and trigger a massive, potentially fatal clumping reaction called agglutination. We absolutely have to match the antigens and antibodies to ensure safe passage.
So the answer here is pretty clear. He can safely receive B negative blood, which matches him perfectly, or he can receive O negative. Type O negative cells lack both A and B antigens, and they lack the Rh factor entirely. Because they have zero identifying antigens on their surface, the patient's antibodies just ignore them completely. And that is exactly why O negative is famously known as the universal donor.
It's all honestly a marvel of biology. So the next time you feel your pulse, ask yourself, are you aware of the microscopic, life-saving traffic jam happening inside your veins right at this very second? Because you've got billions of cargo haulers, highly specialized security teams, and rapid emergency crews fighting to keep your internal highway running smoothly. The sheer volume of coordinated activity is just staggering. Keep that in mind and keep exploring.